Good afternoon, YouTube. Needlebender785 Ohio with a brand new project everybody's been anticipating for the last couple of months. And this is going to be the first video in the series of many. I don't know how many, but it's definitely going to be a good one. Let me just start by saying that this is this project is called the code name for this project is called the Tsunami project, and this is being built in conjunction and partnership with Needlebender 757 out there in Colorado. He's building exactly the same one, and we're sharing our knowledge, mistakes, and everything we learned from this to make bigger and better things out there. So you might want to, if you're not already, subscribe to 757's channel out there. He built some fantastic boxes out there in Colorado. Might as well join. If you miss something here, might catch something over there. But he's going to be building another one of these, and we're just going to be sharing ideas and learning from our mistakes as we go along. But this is going to be one video of many in this series, and this first one will be an introductory video, kind of an overview of what's going to be taking place here. And but we also have a circuit already on the table that I have put together. It's kind of like, I would say, probably the more complicated of this build. But first, let me start by kind of talking about these blowers here a little bit, even though we're just kind of off subject. But EBM blowers, really good high pressure blowers, way better than Dayton from what I found as far as water column goes. Because a lot of guys out there, they'll try to use big CFM blowers, which, if you look at our data sheet, I'm a big data sheet kind of guy. If you look at the data sheet, they don't really produce that. CFM is a no restriction. So when you have a restricted airflow, just like you have with the tube, that CFM goes to zero basically. And this one, I've tested it, went up to 2.4 inches of water column with a special meter I have over here, and just some fantastic airflow coming out of the tube. I mean, these things are not cheap, but they're way better when you're talking about dealing with some really high performance stuff. So kind of just talk about the layout. Let's go over some of the basics. So this is going to be a grounded screen, grid driven amplifier. This is a tetrode, so you have, unlike your triodes, where you have the cathode, you have the screen, which you have the grid, which is grounded, and then the anode, which is your high voltage right here. You have one more potential here, and that's called the screen. Screen sits right here. That's your grid, and then you get your filament here at the bottom. Actually, this is a brand new tube. It just sat around on without any kind of protection from the outside elements, but as you can see, brand new tube. Anyway, this is a 4cx5000 iMac. Good tubes. Anyway, so you have your most negative potential. You have your negative potential, which is your cathode, which is combined with the filament. Then you have your grid, which is should be biased negatively of the cathode, so it has to go below the cathode. Then you have the screen. So if you measure and reference a cathode, it can be anywhere from 500 all the way to 1250 volts above the cathode. And then you have your high voltage, which this is rated up to 7.5 kV. But when we're talking about a grid driven amplifier. These things are phenomenal as far as amplification. I mean, they actually outperform LD Moss when they talk about how low of a drive amplifier we have and we're going to have. But with that kind of power comes great responsibility. So when you talk about triodes, you have a very low gain amplifier. If you really think about it, you have to drive it with a lot of power to get a lot of power. With these things, the maximum, absolute maximum drive we're going to be putting in here is 100 watts. That's what this circuit is rated at. But probably this thing is going to be operated between 20 and 50 watts in. That's where it's going to live. But the rating, my circuit, the one I'm using, is absolute maximum drive is 100 watts. So in order to get that, we have to use something called a balun or an unun. Correct name would be an unun because we're going from an unbalanced to an unbalanced. And we have to have something called a swamping resistor sitting here on the control grid. So when your signal comes into here, which we don't have the input yet, it's actually going to go to a 9-to-1 unun, and it's going to go to a 450 ohm 250 watt RF resistor, which is going to basically show a perfect SWR and plus or minus some losses, but it should be pretty much a flat SWR, which my next video is going to be about that. And this grid is a very high impedance grid, so you have to have a resistor on there to prevent it from kind of going out of control, because these grids and screens are very sensitive to voltage fluctuations and current. So swamping resistor, and then the grid's also going to be biased negatively of the cathode. But the main property of this tube is that the screen, and remember we talked about, it sits about, mine's going to be about exactly at 1,000 volts. That's where I'm running mine from the cathode. So between the cathode and the screen, there's 1,000 volt potential. So, but we're going to call this ground. So this is going to be our case ground. So our cathode, if you flip the whole thing around, is going to be sitting exactly 1,000 volts below ground, below the screen. And our grid is actually going to sit an additional 440 volts below the cathode. So there's going to be high voltage, what I'm trying to say, on both sides of the tube. And this will require 3 separate power supplies, not counting the 12 volts, the one that used to actuate the relays. So you have your high voltage power supply to power the anode. You're going to have a screen power supply, a grid bias power supply, and a cutoff. Bias and cutoff is one circuit, as we're just about to get there. Some nice demonstration I got lined up for you guys here. And then I'm going to have the filament. Oh, I forgot about the filament. The filament transformer is going to be another power supply, and that's actually right here. Right here. There's our filament transformer, 80 amps. Look at the size of those leads. Anyway, so I have several different power supplies, and this socket is actually an iMac socket, came out of a transmitter. But we also have this screen mesh here, which is, even though this is ground right here, since this is our screen, also have an additional ground to prevent any feedback. And this tube is going to be encased in this metal enclosure to prevent any feedback into itself. Because the problem with the grid-driven amplifiers is when you go from cathode-driven to grid-driven, you can run into stability issues if you don't take certain precautions. And trying to mitigate those by having all this extra stuff. Nice. Here's a nice heavy blocker that's going to be here, and if you look underneath there, here's our grounding bars, grounding straps, so grounds the screen to the case, and we also have this all part of the same potential. Something that I haven't mentioned yet, but there's going to be a neutralization circuit, which we'll get to. A lot of people think it's hard, but it actually has only 4 parts in it. It has a high voltage capacitor, a very low value, a higher value that goes to ground underneath the deck. It has a trimmer capacitor and an inductor. That's basically your whole circuit there. Anyway, the rest of the stuff we'll get to, and that's going to be no different than your 3000, or your just going to have a pi tuner and a vacuum relay, that kind of stuff. So in this first video, I decided to kind of cover the guy right here. So this is a grid bias power supply that I just finished putting together, and we're going to go over this thing, and for the demonstration also going to be using our fancy new meters that I made a video about, and the kind of sampling that we're doing, and we're actually going to be running this at real power. This is our screen and grid power supplies. This transformer puts out 330 volts, which gets rectified. It goes to this capacitor, has its own bleeder resistor. This is depowered at the moment. Then you have a shunt regulator right here. You have a resistor, and this puts out exactly 280 volts. Some post-regulation circuitry, and here's the control board itself. As I mentioned, the circuit is depowered. So now let's talk about this board right here. So this is the bias control board. It allows you to adjust the voltage for your Ep.1 operation, which however you want, from negative 260 all the way to 225 with this trim pot right here, and it gives you a nice voltage range to make sure you're an Ep.1 with. You obviously can only do that. I have it set in a ballpark right now, but can do that only when you have a plate meter. This meter is a dual-purpose meter. The bottom is not set up, but the bottom will read screen current from a different power supply. Right now we're not concerned with the bottom, we're just concerned with the top. I have this meter configured as a bidirectional meter, so when there's no current, it's actually reading 0 milliamps right now. And it can source current, and it can sink current, and it'll read both directions on that. Right now I do have a dummy resistor, which is not part of any circuit. The reason why I put that in there is to demonstrate how this meter works. This draws about 64 milliamps, that's what I measured, and we're going to see that as a sourcing current. So I might have to reverse sink versus source. Right now I have source when it's negative. That's all software, not worried about it. So when there's no current, it sits right there in the middle. I have a key on key. So this whole circuit, when it's not keyed up, this tube's in cutoff. So this is your cutoff resistor. All that stuff is in here. When you have this thing mounted, when I'm going to have this thing mounted in there, it's only going to have 2 high voltage wires. It's going to have one wire that's going to go to the cathode, one wire that's going to go to the grid. That's it. Everything else is in here, is all contained, self-contained kind of unit. Right now, and this is the isolated module here. And this is a this part right here. It's like 34 bucks. It's a Hall effect. It's a low current Hall effect sensor. So it has a very good isolation for high voltage, even though this is only dealing with about 400 something volts, but we're dealing with a different ground potential than everything else. Every single one of these supplies is going to have basically reference to a different ground. So it's supposed to have this stuff isolated. So the 12 volts is all going to share one ground, and we can run all these meters from different supplies as long as we isolate them with a Hall effect sensor. You got an op amp to amplify the signal. So it's just the signal is exactly 1/2 of VCC. So this thing works on 9 volts. You got an LM 7809, provides positive 12 volts, and to this thing right here. And the output is very simple. The output there's three pins in there. The output is 1/2 of VCC. Very low current. I think it's like 3 milliamps of current that this can source. So obviously we have to have an amplifier. This is an LM 6142. Very good versatile op amp. There's actually 2 op amps in here. Using a simple non-inverting op amp, variable gain, and a variable offset. The other op amp is used as a buffer, just set up as a buffer. That's all it is, and it just comes out right here, and it goes to here. So all this is totally isolated from any voltage. It's referenced to its own ground. We're going to be reading our voltage over there. The only thing is, since we have this dummy load resistor, it screws up the reading with the tube being in the cutoff, just because this is not supposed to be there. But it is going to read accurate voltage when we key up. Let's see. Okay, now we're going to go hot, and we're going to turn on some stuff. And let's see. We're unkeyed, everything's off, and let's fire this thing up. Alright, so as you can see, we have we're measuring, we're at 0 current, the relay's unkeyed, and this thing is hot. We're going to key up, and we'll see. And we're going to unkey. There you go. When you key up, you can read voltage right there, 242 volts, 243 volts. That's what this is set at. And we are drawing 64 milliamps, just like I talked about. And when you unkey, you hear the relay, and it comes back to 0. Now, for some reason, the tube, current in a lot of these circuits, current can flow in both directions, and this meter will read in both directions, which is very important for our situation. There's the key up. Here's again our voltage. And there we go. Now we're going to turn the high voltage off, unplug it, and watch it bleed down. And there's the remaining of the voltage. Now we're going to do a little safety short out, and this thing has been neutralized. So the DC, the 12 volts is always on, well, at least for now. So this meter always reads 0, no matter what this thing is off or on. Right now everything is depowered as far as the relay as well as the high voltage, and it's been shorted out here on it's also a bleeder resistor for this little cap, and it's this thing runs about 440 volts and on the input side after it's rectified, and it basically you get regulated 225 to 260. That's what the adjustability range of this trim pot. And here's the circuit board the way it looked like when it came from JLC PCB. That's who I use to make my own boards, and again used a program called Dip Trace to design the Gerber files and put it together. And again, there is no circuit like this that you can find online. I had to design the Hall effect and the op amp kind of myself. There was a circuit online for this regulation board. Like I said, had to do some trial and error. This resistor was getting hot and had to use a larger wattage, but everything else worked out really well. This thing runs cool. There is some heat from this obviously, but that's what it's supposed to have. And the other side of this transformer, this is going to be the screen supply. This is much higher voltage, and that has its own power supply, which I'm building over here. This is going to be the screen power supply. A lot simpler circuit. It's also going to have a metering board. It's also going to have its own metering board. I haven't populated it yet, but it's actually identical to this. It's been a cut and paste as far as here's the Hall effect sensor, and this is 7 Zener diodes. So it's very simple. Absolutely. Here's a here's the actual resistor. We called this guy the gold standard. Gold standard. And that guy's going to go right there. And here's the rectifier, capacitor bank, bleeder resistors, and that's going to put out exactly 1,000 volts. Once I get that going, that's going to go in. I'm not going to make a video just on this because this is very simple. Once that goes in there and we have both of these set up where we can test something, I'll do that. But the next video is going to be on the input network. What's that thing called? The resistor on the input, swamping resistor. That's the word I'm looking for. Swamping resistor, balun, and the keying circuitry. But this thing took a couple of weeks to put together, and I had to redo this board twice. Well, actually one. I had to make the board and redo it because the original circuit that I got off on the internet used the optocouplers to isolate the different ground potentials for the meters, and it worked, and there was nothing wrong with it, except for that the optocouplers are not actually non-linear devices. So you can calibrate the meter at the full scale to read whatever you want, but in the middle, as your current changes, they're not going to be linear. So the 100 mil, if I calibrate this on 200 mils, it's going to read perfectly all the way throughout the scale. Optocouplers being non-linear devices, at 10 milliamps, the amplification is a lot more than it is at 200, so it's just very non-linear. So I said, you know what? If I'm going to make something this expensive and put so much work into it, I want an accurate reading meter. So that's when I went with the Hall effect sensor and the op amp. But this is all designed, and if anybody interested, I have the Gerber files. I also have I also sell these boards. If anybody's interested or wants to know how to build one, just shoot me an email, drop me a line or something like that. Anybody who wants to know the values, schematics, or anything like that, I'm planning to share all that along the way. Transformer, talk about this real quick. Here's that. That's a universal transformer from Texas. Great guys over there. Build you whatever you want. I got this custom built for just grid and screen power supply. Anyway, that's about it as far as the first video goes. Appreciate you watching. 73s, and we'll see you in the next one. Needle Bender 785 Ohio. I'm back on the side.